In this example, we're going to try to sketch the graph of this rational function. It's a little bit more complicated, not too bad, but it does involve a little bit more. We have, as you can see, we have two vertical asymptotes here. So our domain is going to go from negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. So we have vertical asymptotes at x equals 2 and x equals negative 2. This is a degree 2 over a degree 2. So we know that we have a horizontal asymptote at y equals 2 over 1. It's that leading coefficient over the leading coefficient. And we have intercepts. So we have intercepts when x is 0, intercepts when y is 0. So when x is 0, we have an intercept of 2 times negative 9, which is negative 18, over negative 4. So when x is 0, we have negative 9 halves, positive 9 halves. Negative 0 over a negative is a positive. Yep, negative over negative is a positive today, so that would be a positive 9 halves. So we'd have 2 times negative 9 over negative 4, negative over a negative. And then, of course, if we put a 0 in for y, we're going to have some x-intercepts. So if we put a 0 in for y, it's all about that numerator being 0, and values of 3 and negative 3 will make that numerator 0. So there we've got some information using our algebra skills from previous courses. Now we're ready to use our calculus skills. So we're going to find our first derivative. It may be easier for you to look at the numerator. Let me move this down. I think I've given myself a little bit of room here. You might have some room that you can just write it on top, but I am going to rewrite this as f of x equals, I'm going to distribute that 2. I could also factor out the 2, find the derivative without the 2, and then multiply it back through. That's actually not a bad idea. Let's try that. Okay, so we have 2, and then I'm going to find the derivative. So the derivative of x squared minus 9 over x squared minus 4, that derivative would be 2x of the numerator times the denominator, x squared minus 4, minus the derivative of the denominator, which is 2x, times the numerator, x squared minus 9. I'm not multiplying by that 2 because I've taken that 2 to the outside, right? So here it is. It's taken to the outside. And then you can see that it would have been multiplied right back through. We're going to keep it on the outside because that's one of our rules from an earlier chapter. All divided by the denominator squared. I'm going to simplify that. I've got 2, and then I'm going to have 2x cubed minus 2x cubed cancels out. I'll have negative 8x plus 18x is negative 10x. Nope, positive 10x. 18 minus 10, or 18 minus 8 is positive 10x. And then that's over x squared minus 4 quantity squared. If I were to multiply that 2 back through, I get 20x over x squared minus 4 quantity squared. Now, 10x, 20x, we're going to set that numerator equal to 0, so the 2 is going to become insignificant. Our critical numbers, or our critical values, are 0, and of course we have plus or minus 2, because those are restrictions from the original domain, and they are restrictions in the first derivative. So we'll make our number line. We'll have -2, 0, and +2. We've done this enough, our first derivative test. Not a bad idea for you to test the values into the first derivative, press pause, and then come back to see what we've got. Not just testing our values, but see if you can locate or identify minimums and maximums. Okay, welcome back. I got the first interval from -∞, -2 to be negative, meaning that in that interval our function is decreasing. -2 to 0, I also got decreasing. From 0 to 2, I got increasing, and then from 2 to infinity, oops, I got increasing as well. There we go. Now at -2 and +2, the original function has vertical asymptotes. So what's happening at 0, when your function goes from decreasing to increasing, you have a minimum. This is going to be a relative minimum, but we'll find that out later for sure. So we put a 0 into the original function, and when we put a 0 into the original function, we get 9/2 out because we actually already did that when we found the y-intercept. Now I would start graphing this, but I really want to know about my concavity. So I'm going to take my function. Now, do you see how we have 20x over x squared minus 4 quantity squared? Just like I took the 2 out, I'm going to take the 20 out. And I'm going to find, so we've got 20 times x over x squared minus 4 quantity squared. I'm going to take that 20 out, and I'm going to find the derivative of this part right here, which is going to involve the chain rule. So not only the quotient rule, but also the chain rule. So the derivative of the numerator is 1 times the denominator minus the derivative of the denominator is 2 times x squared minus 4 to the first power times the derivative of the inside of that binomial, which is 2x. That's the derivative of the denominator times the numerator, all over the denominator squared, and when you square a square, you get the 4th power. So we're going to have 20 on the outside, and I'm going to have x to the 4th minus 8x squared plus 16 minus, actually, before I distribute that, I just noticed that I can factor out, and I can keep this numerator factored, which is going to be easier when I have to set that numerator equal to 0. So let's just keep this here. We've done this problem before. You might recognize it, not the same exact numbers, but we've done it before. So between these two terms, let me highlight them in green and blue. Here's in green, and here's in blue. Between these two terms, they both share an x squared minus 4. So when I factor out that x squared minus 4, I'm going to get an x squared minus 4 left over from that green term minus 2 times 2x times x, which would be 4x squared. So we have 20. This x squared minus 4 is going to cancel out with one of these, so that's going to bring that down to 3. And then we're going to have negative 3x squared minus 4 in the numerator over x squared minus 4 quantity cubed. So now we look for our values that could be potential points of inflection. So we've got our values of, what do we have here? We've got our second derivative. We've got, let's look at this. If I have negative 3x squared minus 4 equals 0, that's not going to give me anything, right? Because x squared equals a negative number. That's not possible. So that's not going to give us any numbers. So the only numbers that we have are those restricted values, negative 2 to 2. So what's happening in our second derivative? What's happening from negative infinity to negative 2? This would be a good place for you to pause and determine if you have concave up, concave down. So check your concavity here and then come back and you can check for accuracy with what I have. Okay, welcome back. I got a negative, which means concave down, and I shouldn't shortcut really anything. Concave down. And then I got a positive, which would be concave up. And then I got a negative, which is concave down. And remember, at x equals negative 2 and positive 2, we have vertical asymptotes. So I think we have enough now to graph a function. So let's do this. Okay, we're just gonna do a rough sketch, maybe go by 2's. So each tick mark will be 2. Let me write that. It's important that I write that for me because sometimes I forget what my scale is. Oh, just like that, I put a 4 and it's definitely a 2. Okay, so each tick mark will go up by 2. I better do that too, because I could see myself going back to 1's instead of 2's. Okay, so our domain, our vertical asymptote, I'm going to graph the vertical asymptotes and the horizontal asymptotes first. So our vertical asymptote, we have at x equals negative 2, and we have another one at x equals positive 2. And then we have a horizontal asymptote at y equals 2. We have intercepts at 3, 0, negative 3, 0, and 0, 9 halves. So negative 3, 0, 3, 0, and then negative 9 halves, which would be negative 4.5. Now we also know that this function is an even function, so that means it's going to be symmetrical about the y-axis, which means the left side will fold right onto the right side of the graph when you fold on the y-axis. That's going to guide us in our graphing. So we can now look at our concavity. We've got our minimum, actually our minimum, this is going to be our lowest point right here. It's going to be, I don't know why I put negative 9 halves. It's positive 9 halves. I think I'm stuck on wanting that to be positive because I did that earlier too, I think. So much better. Yeah, because we have a lot more room up top. So that's going to fit nicely. Okay, so we've got our x-intercepts, negative 3, 0, positive 3, 0, and then 0, 9 halves. Now, we are concave down, and we know that this graph on the left-hand side is going to approach that horizontal asymptote from under. So here is our concave down portion from 0 to negative 2. And then we're going to have concave up. So it's entirely concave up from negative 2 to 2. And this 9 halves is a minimum. So we know that this is what's happening. You know, when we were in a college algebra class, we'd have to do some test points because you had to see whether or not you were doing that or whether or not it was doing something like this, right? Well, now we don't have to worry about that because through our second derivative, we know that this is completely concave up and no points of inflection because our change is occurring at asymptotes. So when your change occurs from at asymptotes, you don't have any points of inflection. So our change in concavity happened at an asymptote right here. So it went from concave down to concave up through an asymptote and then again over an asymptote. And that's our graph. That's actually a pretty good one. It's not a bad one. I'm quite proud of myself when I always wanted to be an artist. So when I draw a graph, although I'm horrible at it because I've just never even given the energy and the time and the effort, I haven't been a hard worker when it comes to art. But when it comes to graphing, I see that as art. I see it as art, and I put a little bit more effort in, and I'm quite proud of my effort and hard work, and you should be proud too, because this is a lot of work right here. It's a lot of work in calculus, but you can see the end result, and that's what calculus is all about. Just lots of hard work and perseverance, for sure. Okay, in the next video, we're going to graph this function right here.